Okay, now we move on to conditional probability. The probability of A, which is what we looked at before, is what? The probability of this shaded area which corresponds to A, or the area A, divided by the total area, which I'm going to shade in blue, which is the entire sample space. So that's how you get probability of A. The red shaded area divided by the blue shaded area. So the important thing is you divided the A shaded area with the entire sample space, which is the entire rectangle, and that's P of A. For conditional probability, let's change back to red. It's probability of A given B. So you are already given B. Let me shade B in red. So if you are given B, it means your sample space, which used to be the entire rectangle, right? This entire rectangle shrinks to the B shaded area. So that's what you're going to divide by now. You're going to be dividing by B and not the entire sample space. But what are you looking for? Probability of A given B. Probability of A, which is just the unconditional probability of A, was A divided by the entire sample space. Here, it's going to be A divided by the reduced sample space, but because you've reduced the sample space, which is because B is given, then you can't have this in A anymore, right? You can't have, let's change this. First clean out this. This can't exist anymore, right? Because it's outside what you are given, which is B. So what part of A can intersect with what you are given, which is B? Let's use highlight. Only this part. So of your A, this is what you're left. So probability of A given B will be this shaded part, the part I just highlighted. And what's that? It's probability of A intersection B, right? The highlighted part is where A intersects B. That's what is left of A, and you divide it by probability of B. So this is precisely, this is precisely what P of A given B is. The given B, it shrinks what you're dividing by. You're dividing by B now. And it also reduces A itself because this cannot exist anymore. And you're left with only this part, which is A intersection B. And that's precisely what you see here. And this is only valid if this is not equal to 0, right? If it's equal to 0, then you're trying to divide by 0, which doesn't work. Good. So that's your conditional probability of A given B. And all of the definitions is spelled out here. So you can read through this. It's basically summarizing all I just explained. You can also have probability of B given A. This was A given B. So what will probability of B given A be? We can sketch it again, say here. This is B given A. So A is given, so it has to be divided by A, right? This is hanging up. Okay, we're back. So you're going to divide by probability of A. What are you going to divide by probability of A? Probability of B given A. B used to be all of this, right? But this part goes away. And you're left with what intersects with A, which is this. So the intersection of B and A is the same thing as intersection of A and B, and this is precisely probability of B given A, which is what is here. So that's how we go about conditional probability. Next thing we talk about here is the law of total probability, and there is a condition for this to apply, and the condition is mutual exclusivity. The events A1 through 4, which we're going to look at shortly, have to be both mutually exclusive and exhaustive. What does that mean? It means A, which is this area, use highlights, which is this area. This is A1. This is A1. It's exclusive, so it's not going to intersect with A2 and the other terms. There is no intersection whatsoever. That's the exclusivity right there. The exclusivity is that they don't overlap. So there's going to be a boundary between each of these. And the last, I just leave it as white. So that's the fact that it is exclusive. How about it being exhaustive? Let me shade the last one. I've used that before. What if we use this? Even though it may not be a good color, but this is A3. What does it mean to be exhaustive? Well, if you add up all the parts I've just highlighted, it basically makes up the entire sample space. That's it being exhaustive. So all of the A sub i's, which is A1, 2, 3, 4, covers the entire sample space, so it is exhaustive. So whenever you have those, both exclusivity and the fact that it is exhaustive, it divides whatever. Let's since we have this taken care of, we can remove all of this. Now you observe it partitions B. So B is this cloud right here. This is B. Those events A through A4 partitions B into these chunks. So this is one, this is another, this is the third, and this is the fourth. So that is what it does to your event B. And now those different chunks, you can write them in terms of probability, right? This is A1 intersection B. It's where A1 bounded here intersects with B. And each of those different chunks are annotated here. So this is A2 intersection B, A4 intersection B, because this is A4 and B is the cloud. So you can write the probability of B, which is all of the cloud, as the sum of these four different chunks, which is precisely what this is. So probability of B, first chunk, which is this, second chunk, which is this, third, and fourth, which is this. So that's what we use to come up with the law of total probability. But there's still one more step. This intersection, we can write it in the form of the conditional probability using our definition of conditional probability. So this equation came from what we looked at on the previous slide. Is what? Probability of B given AI, right? It means you're going to be dividing by AI, what is given. And superscript is going to, the numerator is going to be AI intersection B. And that's precisely, so you can make this the subject of the equation, and you get the probability of this intersection is this product, which is what this is. So we can substitute this equation into this for each of the terms, and that gives you this. For the first term, you have this, because A1 intersection B is PB given A1 multiplied by probability of A1. Then you go to the next term, probability of B given A2 times probability of A2. You're basically substituting 1, 2, 3, and 4. And that's your general equation, which you can write using summation, right? And use AIs. So I, for all i's going from 1 to 4, if there are 4 mutually exclusive and exhaustive events. And this is your law of total probability, which we'll be using to come up with the Bayes rule given here. So what's Bayes rule? Well, before we come up with Bayes rule, let's say why it's very important. And this is very important. It's because it allows you to compute conditional probabilities given another conditional probability. What does that mean? If you are given probability of B given A, how do you find probability of A given B? That's what Bayes rule gives you. You know this, you're trying to find this, you use Bayes rule. And you can get it very simply from the definition of conditional probability. So we looked at this already. Probability of A given B is probability of the intersection between A and B divided by probability of B. You're given B, so you divide by B. Interesting thing is you can also write probability of B given A, which I talked about before. So it's also going to be A intersection B, but now you're given A, right? So you're dividing by probability of A. What does that mean? It means you can substitute this, which is what? It's going to be PB given A, right? We're just multiplying this and this, times P of A, which is marginal probability of A. So you can substitute this in this, and that gives you exactly what is written here, right? So instead of probability of A intersection B, we have written probability of B intersection A times probability of A, and you're still dividing by probability of B. And if you see that, this is what you're looking for, right? This is what is unknown. This is what is given. So using probability of B given A, you can find probability of A given B. And this is precisely Bayes rule. But there's one more step. We can use the result from the previous slide, right? Doesn't allow me to go back. We can use the result from the previous slide, which is the law of total probability, to open up probability of B. Except that instead of having 4 different mutual events like we had before, now we actually have just one event A. So everything else outside A is A complement. So A and its complement will be exhaustive and mutually exclusive because there's no intersection between A and its complement. And because they are mutually exclusive and exhaustive, we can use the law of probability, law of total probability, which we gave before in this form. So this is A1 and this is A2. And that's all you have. And you can put that in place of probability of B in the denominator. And that's your final form of the Bayes rule. Again, what's it used for? If you're given this, you can find this. Given a conditional probability, you can find the other form of the conditional probability. Now, let's look at one final example. A rectangle plastic cover for a compact disc tray has specified length and width. Length is X, width is Y. And we take the integer value. So they will be discrete and not continuous. Possible values of the length, just 3. possible values of the width, just two, 15 and 16, and they are all discrete. So they are jointly discrete, right? And we're given all possible combinations of this length and width in this table, the corresponding joint probability. So if the length is 129 and it's 15 millimeters wide, this is the probability corresponding to that. If it's still 129 in length but 16 in width, the probability is 8%. And giving each of the joint probabilities for all possible combinations of these three lengths and these two widths. The question is, find the probability that a CD cover has length 129. Yeah, probability that a CD cover has length 129 millimeters. That's first question. Second question is find the probability that it has a width of 16. And it's really easy to find. Since you've covered the entire possibilities, you need to just sum up the probabilities where it has a length of 129. So where does it have a length of 129? Here and here. That's it. Everywhere else, it's more than 129. So these are the two conditions where it's 129. So you basically need to just add up these corresponding joint probabilities and you will get the marginal. And what's the sum? 0.12 plus 0.02 is going to be 20%. That's the answer to the first one. Second question is also going to be similar, right? All the cases where it's 16 millimeters wide, which is this, this, and this. So you're going to be adding up. Let's first remove these. So what values are we going to be adding up? Corresponding probabilities, right? So what's 0.08 plus 0.028? That's 0.36. Add 0.36 to 0.04. It's going to be 0.4. So 40% is the answer to that. Now to make it more intuitive, we can actually rearrange this table you're given in this form, which shows the length on the rows and the width in the columns. So width of 15 and 16 are shown in the column. Lengths 129, 130, 131 are shown in the rows. So when you're looking at this value, for instance, it has y of 15, x of 129. This is y of 15, x of 130. This is y of 16, x of 131. And now it's very easy to see that you can sum up across the rows and you get the marginal probabilities of x. Sum across the columns. Is that right? No. Sum across the columns. You're going across columns when you're going this way. This is across columns. This is across rows. So you're summing across rows to get the marginal probabilities of y. Summing across columns to get the marginal probabilities of x. So the question was marginal probability of x being 1 to 9. So you sum across columns and you get the 20%, which I showed before. And the second was marginal probability of y being 16. Sum across rows and you get the 40%, which I showed before. And these are marginal probability mass functions and not PDFs. Why? Because you're looking at discrete values. We were told these are all discrete. You see no decimal places. So this formalizes all I just explained. You sum across, for X, you sum across rows. For Y, you sum across columns. And you can also observe that all of this will sum up to 1, which is the joint probability, the property of the joint probability mass function is that you can sum across both rows and columns, sum everything up is going to be 1. And we already know the marginal probabilities also will sum up to 1, which is what you see. 0.6 plus 0.4, 1. 70 plus 20 plus 10, 100%. And that brings us to the end of this